¿Ya empiezo? Papá, ¿ya empiezo? Ok, ¿ya empiezo? ¿Ya empiezo? Ok. Okay, wait. Hi to everyone. Today my presentation is on convolutional neural networks and FPGA acceleration. So basically implementing convolutional neural networks, which are typically implemented in the software level and performed at the hardware level by CPUs or GPUs, using the FPGA's customizable hardware to implement these very advanced AI tools. So deep learning for facial recognition is one of the uses, and neural network acceleration on the FPGA can allow the streamlining of some parts of the implementation of the algorithm. So you get AI accuracy with real-time speed. This presentation explores how convolutional neural networks are used for facial recognition and how FPGAs can accelerate these calculations. They offer great accuracy, but they require a lot of processing, and FPGAs allow these models to run with low latency and low power consumption, exploiting the customized hardware that's available through these customized chips. The combination of both technologies powers smart cameras, robotics, and embedded systems. Why does facial recognition matter? Facial recognition matters because it's used in all kinds of security and access processes. It automates identity verification, and in smart cities and in vehicles, it becomes a key part of the edge computing necessary to facilitate the functionality. Facial recognition has become a critical application of computer vision. It facilitates passwordless access and improves the user experience, with various sectors of the industry depending on it for their workflows. What is a convolutional neural network? A convolutional neural network is a neural network that specializes in imaging. It learns from spatial patterns and automatically uses filters, activations, and deep layers to understand an image and create a numerical representation of that image. A CNN processes images efficiently. Instead of programming manual rules, the network learns directly from the pixels, with the first layers detecting edges and textures, while deep layers recognize complex structures. This makes CNNs very powerful for ranking and recognition. What kind of facial image input is allowed in a CNN that's implemented in FPGA? So typically, an image is resized to a fixed size, they normalize the RGB values, and then it gets sent to the first convolutional neural layer. Before processing, the facial image is prepared for the network. It's usually set to a certain resolution, and the colored values are normalized. This improves training and inference stability. Thus, a convolutional neural network focuses on facial structure and not on differences in scale. Convolutional layers. They are small filters that scan the image and they detect characteristics such as edges, lines, and textures, and generate feature maps. So they apply a filter over a small region of the image, taking a stride that iterates the filter over the entire image and detects vertical lines, corners, and contrasts, with many filters working in parallel to create different activation maps, and these results feed into deeper layers. Activation functions. They introduce nonlinearity. The ReLU is the most common and allows for complex patterns. Without activation function, a deep network would just be a linear combination of operations. The ReLU removes negative values and keeps positive. This allows complex relationships within images to be modeled. Retain important features. The computational cost is decreased. The pooling summarizes information for very small regions, and the max pooling selects the highest value of each block. This reduces memory and the required operations. It also helps tolerate the small movements or changes in positions of the face, since it's only factoring in the most relevant points of the image. Hierarchical learning. Initial layers detect edges, middle layers detect eyes and nose, and deep layers identify people. So as you go through the convolutional neural network, the small features and most basic features are detected at the beginning, with middle layers detecting more advanced or abstract features, and deep layers finally being able to identify people. Fully connected layers. They combine the extracted features, they generate the final odds, and then they make the identity decision once a representational vector is created. After the convolutional layers, the information moves into dense layers, and these combine all of the characteristics learned, with the final output can represent the identity or a vector of comparison. And this is where the main classification occurs. The training of the convolutional neural network. So to train the convolutional network, is repeated many times. The training is very expensive, but later inferences could be very quickly. So the real challenges: lighting variations, changing in angles and pose, goggle mass or occlusion, facial recognition in the real world presents significant difficulties, where the person may appear turned, shadowed, or out of focus, but objects such as glasses and masks hide key features. This is why it's important to train with diverse data. Why hardware acceleration? The CNN requires millions of operations. The CPU may be insufficient, and edge devices need efficiency. The CNN performs a lot of multiplication and addition, and in real-time systems, a traditional CPU can fall short. So many devices need to respond quickly and with low power, and that's where dedicated acceleration through the architecture comes in. So what is an FPGA? It's reconfigurable hardware, massive parallel processing, customized low latency. So it contains programmable blocks, memory, and DSP drives, digital signal processing, unlike a CPU, and it can run many operations simultaneously. In addition, the data flow can be designed specifically for a convolutional neural network, which makes it ideal for an embedded AI. So CPU versus GPU versus FPGA. A CPU offers flexible control, whereas a GPU is a high parallel performance, and an FPGA is an efficient custom pipeline that balances power and throughput. Each platform has different advantages. The FPGA excels in low latency inference and controlled consumption. Pipeline CNN and FPGA. Each layer becomes a stage, the continuous flow of data, and multiple layers activate simultaneously to allow for a lot of parallelism and a high amount of throughput. By channel partitioning and partitioning by filter. So CNN computing can be divided into multiple parallel modules, with some architectures separating entire layers, with others separating input channels or individual filters. This improves concurrency and speed. Successful partitioning depends on the available resources. Memory bottleneck. Feature maps are great if local cache improves performance. Many times the main problem is not calculation but memory. Reading data from external DRAM consumes time and energy. Saving intermediate results to internal memory speeds up the system. Memory design is critical. DSP blocks, integrated multipliers, ideal for multiply accumulate operations, perfect for convolution. So modern FPGAs include specialized DSP blocks. These perform multiplication and accumulation with a great efficiency. Since the DSPs are like the horsepower of a FPGA, since they will allow you to create deep layers implement deep layers of CNNs on an FPGA based on how many DSP blocks it has. Quantization. Convert float to fixed, lower memory usage, increase calculation speed. Many FPGA's accelerators use fixed point numbers instead of floating. This reduces data size and hardware complexity. If done correctly, the loss of accuracy is small, and it's a key optimization. Variable accuracy. Different layers use different bits, smart resource savings, and balancing speed and accuracy. Not all layers need the same numerical precision. Some require more bits and some less. This allows you to save logic without affecting your accuracy too much. It's an advanced design strategy. Residual networks. Deeper models, better accuracy, more complex flow. Residual networks use direct connection between layers. This allows you to train deeper networks with better performance. An FPGA's ever-reduced additional pass requires a careful design. The benefit often justifies the complexity. Real-time video. Continuous camera processing, frame-by-frame detection, immediate identification. Many systems use live video instead of static photos. Hardware must process constant streams without stopping. FPGAs are ideal for streaming workloads. This enables intelligent surveillance, and automatic access. So the importance of latency. Doors should open up fast. Security requires immediate reaction, and it improves user experience. So the key advantage of edge AI computing is that with FPGAs, you can have a very low latency, as you can see in this, with the number of filters being increased up to 64, and the FPGA in blue maintaining a similar amount of performance when compared to a GPU that, despite its increased amount of parallelism, doesn't have the same amount of efficiency and when it comes to its latency and throughput. Energy efficiency. The lower consumption of the GPU in most cases, and it's ideal for edge AI since it reduces heat and costs. And the energy consumption limits many AI products, including batteries, ventilation, and temperature, all affecting feasibility. FPGAs offer a good performance to watt ratio. Design. Accuracy versus speed, resources versus parallelism, flexibility versus efficiency. There is no perfect architecture. More precision consumes more resources, more parallelism accelerates, but occupies more area, and engineers are constantly balancing these factors. Use cases. There's intelligent access control, industrial identification, and commercial analytics. The CNN and FPGA combination has clear applications. Smart buildings can validate identity instantly. Factories can control restricted areas, and businesses can analyze customer flow. Future trends are in smaller models, a hybrid of CPU and FPGA systems, and better automatic tools. The future points to more compact AI running close to the sensor, hybrid systems which will mix CPU control and FPGAs for acceleration. New tools will simplify development. So the risks and ethics are in facial data privacy, algorithmic biases, and a need for strong security. It should be used responsibly with sensitive data requiring strict protection. It is also important to avoid bias in training, with technical success is not enough without ethics. So conclusions are: the CNN revolutionized computer vision, the FPGA accelerates inference efficiently. Together they will enable AI in real time. And CNNs have changed the way images are analyzed. FPGAs allow these models to be run efficiently and quickly. And together they create powerful solutions for the real world. They are a strategic combination for the future. Thank you very much. And any questions, please? Yeah.